The camera opens so close that the world is reduced to polished black armor and a single gleaming point. Suspended beneath the abdomen, the wasp's stinger fills the frame like a hypodermic needle forged from living tissue, its surface smooth, its tip honed to a microscopic edge. Sunlight catches it for an instant, and in that instant the response it provokes is almost involuntary. Muscles tense. Breathing shortens. Even without contact, the body recognizes the threat. This is not fear born of imagination, but a reaction wired deep into mammalian nervous systems, shaped by millions of encounters between soft flesh and venom-tipped insects. The wasp does not need to strike to be understood. The mere presentation of the weapon is enough to alter behavior, forcing distance, caution, retreat. In the warm air of late summer, the wasp hovers near a fallen apple, its wings vibrating so quickly they blur into transparency. Around it, the ecosystem hums with competing interests. Ants work the fruit's surface, flies arrive in erratic bursts, and the wasp surveys the scene with compound eyes that fragment motion into rapid snapshots. It does not rush. Its movements are controlled, economical. The stinger remains retracted, hidden beneath overlapping plates, because deployment is costly. Venom is not an unlimited resource, and the act of stinging is not a reflexive outburst, but the final step in a structured escalation process that balances risk, reward, and survival. The stinger itself is a remarkable evolutionary invention, a transformed ovipositor repurposed over deep time from egg-laying to chemical injection. It is not a single spike, but a complex assembly of sliding shafts and barbs that move against one another, allowing the tip to penetrate tough skin with minimal force. Unlike the fangs of snakes or the jaws of predators, this tool does not rely on strength. It relies on precision. The venom travels down narrow channels, driven by muscular contractions that regulate dose with surprising control. The amount delivered is small, measured in micro quantities, yet its effect on a much larger animal can be profound, triggering pain, inflammation, and in some cases, a cascading immune response that overwhelms the victim's physiology. This imbalance between dose and effect is the wasp's greatest advantage. Venom is expensive to produce, metabolically demanding, and tailored to disrupt nervous and cellular processes rather than to kill outright. For most wasps, the goal is not death, but deterrence. Pain is the message. It is a biological broadcast that says retreat now or pay more later. In mammals, that message travels fast, carried by nerve fibers that evolve to prioritize damage avoidance. The sharp burning sensation is followed by a throbbing ache that lingers, reinforcing the lesson long after the wasp has flown away. From an ecological perspective, this is efficiency refined to its highest level. A tiny insect alters the behavior of animals thousands of times its size, without needing to overpower them physically. Yet the stinger is rarely the first signal. Before injection comes posture. The wasp raises its abdomen, angles its body, and pivots to keep the threat in view. Wings flare slightly, not for flight but for display, amplifying its silhouette. Chemical cues seep into the air as alarm pheromones, invisible but potent, warning nearby nestmates, and escalating the encounter from individual defense to collective readiness. This sequence is deliberate. The wasp tests boundaries, probing whether intimidation alone will suffice. Many potential predators, from birds to mammals, have learned to recognize these signals and back away. In those moments, the stinger remains unused, its purpose fulfilled without being unsheathed. The logic behind this restraint becomes clear when viewed through the lens of survival strategy. For a solitary predator, injury can mean starvation. For a social wasp, losing a worker still carries cost. But the colony's investment in venom and time demands efficiency. Escalation allows the wasp to minimize risk while maximizing effect. Only when warnings fail does the final step occur, and when it does, it is executed with precision rather than fury. The wasp strikes, injects, and disengages, often in less than a second, reducing exposure to retaliation. This is not aggression for its own sake. It is calculated defense embedded in instinct. Around the nest, this strategy scales dramatically. Paper combs cling to eaves or tree branches, fragile structures housing larvae that cannot flee. Here, the stinger becomes part of a broader defensive network. Guards patrol the perimeter, responding to vibrations and shadows. When a threat approaches, alarm pheromones spread like an invisible shockwave, mobilizing dozens of defenders. In these moments, escalation accelerates. Warning postures overlap, and the air fills with rapid wing beats. If contact occurs, multiple stings can follow, each delivering venom calibrated to amplify pain and confusion. The goal is not to kill the intruder, but to overwhelm its senses and drive it away from the vulnerable core of the colony. The venom itself reflects this purpose. Rather than targeting vital organs, it activates pain receptors and inflammatory pathways, creating immediate feedback that the encounter has crossed a dangerous threshold. In some species, the venom composition is tuned to different predators, exploiting weaknesses in their nervous systems. Birds experience sharp, localized pain. Mammals feel a deeper, spreading burn. Even reptiles and amphibians are not immune, their slower metabolism still registering the chemical intrusion. This versatility explains why the wasp's stinger has remained effective across environments and eras. It is not a blunt instrument, but a modular one, adaptable to a wide range of adversaries. Seen from this perspective, the wasp is not reckless, nor is it cruel. It is an organism navigating a crowded and competitive world, armed with a tool that allows it to defend itself and its offspring without constant violence. The stinger's power lies as much in its promise as in its delivery. Most encounters end before injection, resolved through posture, pheromones, and learned fear. When the needle finally appears in full, gleaming and ready, it signals that all previous steps have failed. What follows is not overkill, but necessity, a final measure taken to preserve life by inflicting pain. As the camera pulls back, the wasp retreats to the air, stinger once again concealed. The ecosystem resumes its rhythm. Ants return to the apple. Flies circle cautiously. The lesson, however, lingers. Somewhere in a mammalian brain, neural pathways have been reinforced, associating that slender, living needle with danger. This is how a small insect reshapes behavior on a grand scale, not through domination, but through precision, restraint, and a deep evolutionary understanding of when to strike and when to simply warn. The meadow at midday appears calm, a tapestry of grasses and flowering stems swaying under a steady breeze. But within this apparent stillness, surveillance is constant. Leaves vibrate with insect movement. Shadows pass overhead. Every surface is contested territory. On the underside of a broad green leaf, a shieldbug rests, its body shaped like a flattened dome, edges flared and angular, coloration blending almost perfectly with the plant tissue beneath it. From a distance it seems inert, decorative even, but this stillness is a posture, not a weakness. The shieldbug is alert, its sensory world tuned to pressure changes in the air and vibrations transmitted through the plant's veins. When the threat arrives, it does not come dramatically. A bird lands nearby, claws flexing against the stem. The leaf trembles. The shieldbug freezes, trusting its camouflage for a moment longer. This is the first layer of defense, passive and cost-free. Many predators pass without noticing, scanning for motion rather than shape. But when the bird tilts its head and peers closer, the equation shifts. The shieldbug does not flee. Instead, it deploys a defense that is neither mechanical nor venomous, but chemical, immediate, and unforgettable. A sudden burst erupts from glands along the insect's thorax, a fine spray released into the air in a pale, translucent cloud. Caught in the sunlight, it becomes visible for a fraction of a second, drifting outward like breath in cold air. This is the proof moment, the instant where defense becomes undeniable. The odor arrives before contact, sharp and penetrating, cutting through the green scent of crushed leaves. To human noses, it can resemble rancid herbs or burnt rubber. But to a bird's far more sensitive olfactory system, it is overwhelming. The predator recoils, head snapping back, beak opening reflexively. The shieldbug remains in place, its job already done. This chemical release is not meant to incapacitate. It is meant to teach. Within seconds, the bird lifts off, abandoning the leaf and carrying with it a powerful association between shape, smell, and consequence. The encounter is brief, but its effects ripple forward in time, altering future decisions in ways that favor the shieldbug and its kin. The defensive chemicals of shieldbugs are complex blends of aldehydes, esters, and other volatile compounds, produced and stored in specialized glands. Manufacturing them requires energy and dietary input, which is why the insect does not deploy them casually. But unlike venom, which must penetrate tissue to be effective, these chemicals work at a distance. They enter the predator's sensory world instantly, triggering aversion before physical harm can occur. This makes them especially valuable against birds and mammals, predators that rely heavily on smell and taste to evaluate prey. What makes this strategy particularly effective is not the pain it causes, but the memory it creates. Many predators learn quickly, sometimes after a single exposure. The smell becomes a warning signal, a cognitive shortcut that allows the predator to avoid costly mistakes in the future. In this way, the shieldbug's weapon extends beyond the present moment. It reshapes the behavioral landscape, influencing not just one attacker, but potentially many, as learned avoidance spreads through a population. Within the ecosystem, this creates a subtle but powerful dynamic. Shieldbugs do not need to outrun their predators or overpower them. They rely instead on predictability and consistency. Their distinctive shape and coloration become part of the lesson, reinforced by the chemical signature that accompanies any attack. Over time, predators begin to bypass these insects altogether, selecting for other prey that lack such defenses. This selective pressure reduces mortality for shieldbugs and allows them to invest energy in growth and reproduction rather than constant flight. The effectiveness of this strategy becomes clear when observing predator behavior across seasons. Young birds, inexperienced and curious, are more likely to test unfamiliar insects. They approach shieldbugs more often than adults do, and they are the ones most likely to trigger a spray. Afterward, their behavior changes. They hesitate when encountering similar shapes, veering away before contact. This learning curve benefits not just the individual shieldbug that deployed its chemicals, but the entire species. The weapon is memory, shared and reinforced through repeated encounters. The shieldbug's chemical defense also shapes interactions with other insects. Ants, for example, are persistent predators that rely more on touch and chemical communication than on sight. When an ant encounters a shieldbug, the initial contact may provoke a spray, contaminating the ant's antennae and disrupting its ability to communicate with nestmates. The ant retreats, grooming itself intensely to remove the chemical residue. This delay can be enough to prevent recruitment, sparing the shieldbug from being overwhelmed by numbers. Despite its effectiveness, the chemical defense is not limitless. Glands take time to refill, and repeated use can leave the insect temporarily vulnerable. This constraint encourages selective deployment. The shieldbug assesses threats through vibration patterns and pressure changes, reserving its spray for encounters that cannot be resolved through camouflage alone. This measured response mirrors broader ecological principles, where energy expenditure must always be weighed against survival benefit. The chemistry itself is finely tuned. Volatility ensures rapid dispersal, allowing the odor to reach predators quickly. Persistence ensures that it lingers just long enough to be remembered without saturating the environment. Too weak, and the lesson would not stick. Too strong, and the insect might attract unwanted attention from specialized predators that can tolerate or even exploit the chemicals. Evolution has balanced these factors, producing a deterrent that is effective across a wide range of contexts without destabilizing the shieldbug's niche. As the day progresses, the meadow resumes its rhythm. Pollinators move between flowers. Spiders reset their webs. The shieldbug remains on its leaf, the chemical cloud long dispersed. To an observer, nothing seems to have changed. But beneath the surface, the ecosystem has adjusted. A predator has learned. A pathway in its brain has been rewired, associating a particular smell and shape with discomfort. This invisible shift is the true impact of the shieldbug's defense. In this light, the shieldbug represents a different philosophy of survival. It does not rely on speed, strength, or lethality. It relies on cognition, not its own, but that of its enemies. By exploiting the learning capacity of predators, it turns their intelligence into a shield. Each encounter reinforces a boundary that predators are reluctant to cross again. Over generations, this dynamic stabilizes populations, allowing shieldbugs to persist in open habitats where escape would be difficult. As evening approaches and light angles soften, the shieldbug finally moves, repositioning itself as temperatures drop and moisture rises. Its chemical glands begin the slow process of replenishment, synthesizing the compounds that may be needed again tomorrow. The meadow grows quiet, but the lessons embedded within it endure. Here, survival is not always about overpowering the enemy. Sometimes it is about being remembered. Morning light spills across a hedgerow, warming dew-beaded leaves and coaxing movement from a landscape that spent the night in stillness. On the broad surface of a nettle leaf, a ladybug crawls slowly, its rounded shell catching the sun in flashes of red punctuated by black spots. To the human eye, the insect appears almost ornamental, a symbol of harmlessness placed gently into the green. Yet this brightness is not decoration. It is a declaration, visible from a distance and backed by chemistry that turns curiosity into regret. The ladybug's world is exposed. Unlike insects that hide beneath bark or within soil, it forages openly, searching for aphids clustered along tender stems. This openness would be an invitation to predation, were it not for a defense system that operates before jaws can close. The ladybug's coloration functions as a warning label, a visual signal that advertises chemical protection. Birds, reptiles, and small mammals scanning the vegetation learn to associate this pattern with an unpleasant experience, often after a single encounter. The message is simple and consistent. This prey is not worth the effort. When that message is ignored, the ladybug escalates. As a bird's beak nears, the insect stiffens, legs pulling inward as pressure builds within its body. Tiny joints at the knees flex, and a yellowish fluid seeps out, pooling briefly before spreading across the shell's surface. This is reflex bleeding, a defensive response that releases hemolymph laced with bitter alkaloids. The timing is critical. The release occurs at the moment of contact or just before, coating the mouthparts of the predator and flooding its taste receptors with a chemical shock. The effect is immediate. Birds recoil, shaking their heads, wiping beaks against branches in an attempt to rid themselves of the taste. The ladybug often survives these encounters intact, dropped rather than swallowed. This outcome is the true measure of success. The goal is not to kill the predator or even to injure it, but to interrupt the attack at its most vulnerable point before the bite becomes fatal. Chemistry wins by stopping the sequence early, transforming a lethal encounter into a lesson learned. The compounds responsible for this defense are derived from the ladybug's diet, particularly the aphids it consumes. By feeding on insects that themselves sequester plant toxins, ladybugs incorporate these chemicals into their own tissues, modifying and storing them for later use. This process links the ladybug's survival directly to the plants and herbivores around it, embedding it within a web of chemical relationships that spans multiple trophic levels. The toxins do not harm the ladybug, which has evolved mechanisms to tolerate and compartmentalize them, but they remain potent deterrents to would-be predators. Reflex bleeding is costly. Losing hemolymph means losing nutrients and water, resources that must be replenished through feeding. Repeated use can weaken the insect, making it more vulnerable to environmental stress. This cost reinforces selective deployment. The ladybug does not bleed at every disturbance. Light touches or vibrations may trigger stillness or flight instead. Only when physical contact threatens does the chemical defense activate, ensuring that the investment yields maximum survival benefit. The bright coloration that accompanies this chemistry amplifies its effectiveness. Known as aposematic coloration, it serves as a visual shorthand in the predator's brain, reducing the need for repeated testing. Once a bird has experienced the taste of a ladybug, the red and black pattern becomes a signal to avoid similar prey in the future. This learned avoidance can persist for months, sometimes for life, protecting not just individual insects, but entire populations. In this way, the ladybug's defense extends beyond chemistry into cognition, shaping predator behavior at the community level. Within the ecosystem, this has cascading effects. Predators shift their focus to less defended prey, altering insect population dynamics. Aphid numbers may fluctuate in response, influencing plant health and growth. The ladybug's success as a predator of aphids is therefore intertwined with its success as prey that cannot be easily consumed. Its chemical defense allows it to occupy an exposed niche, hunting openly where stealth would be ineffective. And in doing so, it exerts control over herbivore populations that might otherwise overwhelm vegetation. The strategy is not without its limits. Some predators, particularly those that rely less on taste or that have evolved tolerance to toxins, can still consume ladybugs. Certain birds learn to remove the shell quickly, minimizing contact with the chemicals. Others simply endure the taste when food is scarce. These interactions drive ongoing evolutionary adjustments, fine-tuning toxin composition and concentration across different species and habitats. The ladybug's defense remains effective not because it is absolute, but because it stays one step ahead of most attackers most of the time. From a physiological perspective, reflex bleeding is a rapid response system, integrating sensory input with muscular action and chemical release. The insect's nervous system detects pressure and triggers muscular contractions that force hemolymph outward through weak points in the exoskeleton. This coordination occurs in fractions of a second, demonstrating how even small insects possess finely tuned control over complex defensive mechanisms. The simplicity of the behavior belies the sophistication of the underlying biology. As the day warms, the ladybug resumes its search for aphids, climbing stems and probing leaf undersides. Its shell dries, the chemical residue evaporating, but the warning remains. Predators that witnessed or experienced the defense earlier in the season now bypass the insect entirely, their attention drawn instead to less conspicuous prey. The ladybug's survival is secured not through escape, but through recognition. In this system, the ultimate victory is prevention. The chemistry does its work before the kill, interrupting the predator's decision-making process at the critical moment. By the time jaws close, it is already too late for the predator to commit. The ladybug falls back into the vegetation, alive, its lesson delivered. Bright colors glint once more in the sun, not as an invitation, but as a boundary, clearly marked and chemically enforced. At the edge of a sun-warmed forest clearing, where fallen seeds gather in the cracks of dry soil and the air carries the faint resinous scent of trees, movement concentrates in unexpected places. At the base of a linden trunk, a cluster of firebugs spreads across the bark like scattered embers. Their bodies are sharply patterned in red and black, the contrast so strong it seems almost artificial against the muted browns of the ground. They are not hidden. They are not dispersed. They gather openly, dozens at a time, each insect reinforcing the same message through color, proximity, and chemical potential. From above, a bird surveys the clearing. Its vision is tuned to movement and contrast, and the firebugs register immediately, not as individual prey items, but as a single, conspicuous signal. This visibility is deliberate. Firebugs do not rely on speed or secrecy to survive. Their defense begins long before contact, built on the principle that being seen can be safer than being overlooked if what is seen communicates risk. The red and black patterning is a warning, but unlike solitary insects that advertise danger alone, firebugs amplify this signal through numbers. Each firebug carries chemical defenses derived from compounds in the seeds it consumes, particularly those of plants that produce protective toxins to deter herbivores. These chemicals are stored within the insect's body and can be released when threatened, producing an unpleasant taste and odor. On their own, a single firebug's defense might be ambiguous to a predator encountering it for the first time. The taste would be foul, but the lesson might be weak. In a group, however, the effect is multiplied. A predator that samples one insect in a cluster experiences not just the chemical shock, but the visual context of many identical insects nearby. The association between appearance and unprofitability becomes stronger, faster, and more durable. Clustering transforms individual defenses into a collective statement. When a bird pecks at one firebug and recoils, it does not see an isolated mistake. It sees an entire patch of prey, bearing the same colors, shapes, and behaviors. avoidance follows quickly. The predator learns not simply to reject one insect, but to exclude an entire category from its diet. This is the essence of group warning chemistry. The chemical defense exists, but its power lies in how it is advertised and reinforced through social arrangement. The benefits of this strategy ripple outward. By clustering, firebugs reduce the likelihood that any one individual will be tested repeatedly. The first encounter carries the cost of chemical deployment, but subsequent encounters are often avoided altogether. This lowers the overall energy expenditure required for defense, allowing the insects to invest more in growth and reproduction. In environments where resources can be patchy and seasonal, this efficiency matters. The firebugs remain near food sources, feeding and mating in relative safety, while predators adjust their foraging routes accordingly. The chemical component of the defense is subtle but effective. Firebugs do not possess potent toxins capable of causing lasting harm. Instead, their chemicals create a sensory experience that is reliably unpleasant. The taste lingers just long enough to be memorable without overwhelming the predator's system. This balance is crucial. A defense that is too mild fails to teach. One that is too severe might provoke more determined attacks from predators that adapt or tolerate the compounds. Firebugs occupy a middle ground, where deterrence is consistent and predictable. From an ecological perspective, this strategy demonstrates how honesty in signaling can be more effective than brute force. The firebug's colors accurately reflect its chemical defenses. Predators that heed the signal benefit by avoiding wasted effort, while firebugs benefit by being left alone. Over time, this mutual understanding stabilizes interactions between species. The signal remains reliable because cheating would be costly. An insect that mimicked the colors without the chemistry would be quickly discovered and consumed, reinforcing the integrity of the system. The clustering behavior itself is not solely defensive. Firebugs gather around shared resources, particularly seed-rich areas, where feeding efficiency increases. Proximity facilitates mating and reduces the energy spent searching for partners. Defense, reproduction, and feeding converge in the same behavior, illustrating how multiple selective pressures can shape a single coherent strategy. The warning signal becomes stronger, not because of any single adaptation, but because several align in the same direction. Predators respond accordingly. Young birds, inexperienced and driven by curiosity, may still test a cluster. Their first peck delivers the lesson. Adults, having learned earlier, often bypass the group entirely. This learned avoidance can spread culturally within predator populations as juveniles observe adult foraging choices. In this way, the firebug's defense extends beyond individual encounters, influencing predator behavior across seasons and generations. There are moments, however, when the system is stressed. During periods of scarcity, predators may take risks they would normally avoid. In these cases, the group defense still offers advantages. A predator that consumes one firebug may be less inclined to continue, deterred by the cumulative effect of taste and smell. The cluster ensures that even if some individuals are lost, the overall signal remains intact. Survival here is not about invulnerability, but about tipping probabilities in favor of the group. The effectiveness of this strategy underscores an important truth about ecological weapons. Not all defenses are about causing harm. Many are about shaping expectations. The firebug's weapon is not poison in the dramatic sense, but credibility. The signal is believable because it is backed by experience, reinforced by repetition, and broadcast clearly through color and aggregation. Predators learn quickly because the information is unambiguous. As the afternoon light shifts and shadows lengthen, the firebugs remain in place, their colors still vivid against the bark. They do not scatter when a breeze passes or when distant footsteps disturb the ground. Their confidence is not arrogance, but assurance born of consistency. The ecosystem around them has adjusted. Predators have learned. Paths have changed. The clearing holds its balance. In the end, the firebug's survival story is one of cooperation, not in the social sense of complex hierarchies, but in the alignment of individuals around a shared message. Together, they speak louder than anyone could alone. Their chemistry supports the signal, but it is the signal itself that does the work. In a world of constant threat, sometimes the most effective weapon is not what you carry inside, but what others believe you to be. As the sun climbs higher over cultivated fields and roadside vegetation, the landscape reveals pockets of intense color that seem almost deliberate in their placement. On the broad leaves of hibiscus and cotton plants, clusters of red cotton bugs assemble in open view, their bodies saturated in red, edged with stark black markings that cut sharply against green foliage. There is no attempt to hide, no retreat into shade. Instead, the insects remain exposed, motion slow and confident, as if daring the world to notice. And the world does notice. From the perspective of a predator scanning the vegetation, these insects are impossible to ignore. Vision, especially in birds and reptiles, is tuned to contrast, and the red cotton bug exploits this bias fully. The signal does not rely on subtlety. It overwhelms. Against the background noise of leaves and stems, the clustered insects form a visual interruption, a block of color that demands attention. This is not accidental. Visibility itself is the foundation of their defense, and unlike solitary warning systems, this one gains strength through repetition and scale. Each red cotton bug carries chemical defenses derived from its diet of plant seeds rich in secondary compounds. These chemicals render the insect distasteful and mildly toxic to many predators, enough to discourage consumption without requiring lethal potency. But the true power of this defense lies not in the chemistry alone. It lies in how that chemistry is advertised, reinforced, and remembered. The red cotton bug does not simply possess deterrents, it communicates them. Clustering amplifies this message. A single insect might be sampled, bitten once before being rejected. A group, however, presents a unified signal that collapses uncertainty. When a predator approaches a cluster, the probability of repeated negative experience rises sharply. One bite becomes many tastes. One bad decision becomes a pattern. The predator does not just learn that one insect is unpleasant. It learns that an entire visible group represents the same mistake, multiplied. This social visibility transforms defense into a collective phenomenon. The insects benefit from each other's presence, not through cooperation in the traditional sense, but through shared signaling. Each individual reinforces the credibility of the others. The message becomes unavoidable because it is everywhere the predator looks within that patch of habitat. Even a predator inclined to test unfamiliar prey is quickly overwhelmed by repetition. The visual cue is burned into memory alongside the chemical consequence. In this system, chemistry is only half the story. The deterrent compounds are effective, but they do not need to be extreme. The goal is not to incapacitate, but to educate. The predator's nervous system does the rest, forming associations between color, grouping, and outcome. Once established, these associations persist, altering foraging behavior long after the initial encounter. Predators begin to bypass entire plants or areas where red cotton bugs are known to cluster, reshaping movement patterns across the landscape. This has measurable ecological effects. By reducing predation pressure through visibility and signaling, red cotton bugs can remain near food sources for longer periods. They feed, mate, and develop without constant disruption, increasing reproductive success. Their presence, in turn, influences plant communities. Seed consumption affects plant regeneration, while predator avoidance shifts pressure onto other insect species. The red cotton bug becomes a node in a network of indirect interactions, its survival strategy rippling outward into the broader ecosystem. The added twist in this system is the way communication replaces concealment entirely. Many chemically defended insects rely on surprise, releasing toxins only after contact. The red cotton bug inverts this sequence. It announces its defense in advance, broadcasting its unprofitability before an attack begins. The chemistry is communicated through color and aggregation, reducing the need for frequent deployment. This saves energy and minimizes physiological cost, a crucial advantage in environments where resources fluctuate. There is also a temporal dimension to this strategy. Juvenile predators, inexperienced and exploratory, are the most likely to test warning signals. When they encounter a cluster of red cotton bugs, the lesson is swift and decisive. The unpleasant taste is reinforced visually by the presence of many identical insects. As these predators mature, the avoidance persists, shaping behavior across seasons. The insects benefit from a memory they did not create directly, but triggered through repeated, consistent signaling. The red cotton bug's success also depends on honesty. The warning colors must remain reliable indicators of chemical defense. Any breakdown in this honesty would invite exploitation by predators willing to test the signal again. Evolution maintains this balance by coupling visibility with genuine deterrence. The chemistry does not need to be extreme, but it must be consistent. In this way, communication and chemistry remain aligned, reinforcing each other through selection. There are moments when this system is challenged. During food shortages, predators may take risks they would normally avoid. Even then, clustering provides resilience. The loss of a few individuals does not weaken the overall signal. In fact, repeated exposure during scarcity can strengthen predator aversion, as the cumulative unpleasant experiences outweigh the caloric reward. The group absorbs the cost, preserving the long-term effectiveness of the defense. Physiologically, the red cotton bug supports this strategy through metabolic tolerance. The compounds it stores are sequestered in tissues where they do not interfere with normal function. Specialized pathways allow the insect to process and retain these chemicals without harm, converting dietary toxins into defensive assets. This ability reflects a deep evolutionary relationship between the insect and its host plants, one built on exploitation and adaptation over generations. As the day progresses and temperatures rise, the bugs remain largely stationary, conserving energy. Their stillness reinforces the warning signal. Motion might attract curiosity, but immobility paired with bold color communicates certainty. There is no ambiguity here. The insects do not flee, because they do not need to. Their defense has already done the work. In the surrounding environment, predators adjust accordingly. Birds shift their attention to less conspicuous prey. Lizards avoid the plants where red clusters are common. These choices, repeated across individuals and time, sculpt the flow of energy through the ecosystem. What appears to be a simple visual display becomes a force that shapes who eats whom and where. Ultimately, the red cotton bug illustrates a refined survival principle. Defense does not always require escalation. Sometimes the most effective strategy is to be unmistakable. By making themselves highly visible together, these insects ensure that no predator can plausibly ignore the message. Their chemistry is real, but it is the communication of that chemistry that keeps them alive. In a world governed by perception as much as by force, being seen clearly can be the strongest protection of all. The first thing that registers in a summer meadow is motion, a slow, drifting rhythm that seems almost detached from urgency. Against a backdrop of tall grasses and flowering plants, a monarch butterfly moves with deliberate ease, wings lifting and settling in a steady cadence that ignores the nervous tempo of smaller insects. Its coloration is unmistakable. Broad fields of orange framed by deep black veins and bordered with white spotted margins cut through the green like a signal flare. This is not camouflage. It is an announcement, carried lightly on the air. To understand what that announcement means, it is necessary to trace the monarch's story backward, beyond the adult form and into the early stages of its life. Long before the butterfly ever takes flight, the chemistry that will protect it is already being assembled. As a caterpillar, the monarch feeds almost exclusively on milkweed, a plant that has evolved its own chemical defenses to deter herbivores. Milkweed leaves are laced with cardiac glycosides, compounds capable of disrupting heart function in many animals. Most insects cannot tolerate them. The monarch caterpillar not only survives on this diet, but thrives. This ability is not accidental. Through evolutionary adaptation, monarch caterpillars have developed physiological mechanisms that allow them to ingest, transport, and store these toxins without suffering harm. Specialized proteins bind the compounds, preventing them from interfering with the caterpillar's own cellular processes. Rather than breaking the chemicals down, the caterpillar preserves them, sequestering the toxins in its tissues as it grows. What the plant evolved as a defense becomes, in the monarch's body, a resource. As the caterpillar transforms into a butterfly, this chemical inheritance is carried forward. The toxins persist through metamorphosis, redistributed into the adult's body, wings, and fluids. The monarch does not synthesize its own poison, it borrows it. This distinction matters because it ties the butterfly's survival directly to the presence of its host plant. Without milkweed, there is no chemical shield. The monarch's life history is therefore inseparable from the plant communities it inhabits, binding insect and vegetation into a tightly linked ecological relationship. When a predator encounters an adult monarch, the consequences of this relationship become clear. A bird that snaps at the butterfly mid-flight may succeed in catching it, but the bite rarely ends there. Almost immediately, the taste triggers rejection. The cardiac glycosides produce nausea and discomfort, sometimes severe enough to induce vomiting. The predator releases the butterfly, often too late for it to recover, but the experience imprints itself deeply. The predator learns not just that monarchs are unpleasant, but that their appearance predicts that outcome with high reliability. This is where the monarch's coloration becomes critical. The orange and black pattern is not arbitrary. It is a visual code, evolved to be highly visible across a wide range of lighting conditions and habitats. Against foliage, sky, and earth, the contrast remains strong. Predators do not need to sample repeatedly to confirm the association. One encounter is often enough. The pattern becomes a universal warning, recognized across regions and, remarkably, across species. The effectiveness of this warning is enhanced by the monarch's behavior. Unlike insects that dart unpredictably or hide in dense cover, monarchs fly openly, even leisurely. This confidence is not carelessness. It is reinforcement. By remaining visible, the butterfly ensures that predators have ample opportunity to see and remember its distinctive pattern. Avoidance becomes the default response, not the result of constant testing. Within predator populations, this learning spreads. Young birds observe adults ignoring monarchs, bypassing them in favor of less conspicuous prey. Over time, the orange and black pattern becomes embedded in collective memory. This shared understanding reduces predation pressure not only on individual butterflies, but on the species as a whole. The chemistry borrowed from milkweed is broadcast visually, amplified through repetition and consistency. The monarch's strategy also influences other insects. Some species mimic the monarch's appearance without possessing the same chemical defenses, exploiting the established warning signal. This mimicry depends entirely on the monarch's continued honesty. If predators begin to encounter too many palatable imitators, the signal weakens. The monarch's chemical defense anchors the system, maintaining the credibility of the warning across the ecosystem. Beyond defense, the monarch's life cycle introduces another layer of ecological complexity. Monarchs are famous for their long-distance migrations, journeys that span continents and generations. Throughout these movements, the chemical protection remains relevant. In unfamiliar territories, predators may not recognize the warning immediately. The first encounters serve as rapid education, extending the reach of the signal into new environments. The monarch carries its chemical story wherever it goes, teaching predators along its migratory path. The reliance on borrowed chemistry creates vulnerabilities as well. Habitat loss and the decline of milkweed populations directly undermine the monarch's defense. Caterpillars deprived of their host plants cannot acquire the toxins that make adults unpalatable. Butterflies raised on alternative plants may appear identical, but lack the chemical backing that makes the warning effective. Predators sampling these individuals receive a false signal, potentially eroding the learned avoidance that protects the population. This fragility highlights how tightly coupled the monarch's survival is to specific ecological conditions. From a physiological standpoint, tolerating cardiac glycosides requires precise adaptations. These compounds interfere with ion transport in cells, a process fundamental to nerve and muscle function. Monarchs possess modified ion channels that are less sensitive to the toxins, allowing normal physiological operation even in the presence of compounds that would be lethal to other animals. This modification represents a fine balance. The toxins must remain potent to predators while being neutralized internally, a dual requirement that has shaped monarch biology at the molecular level. In the broader landscape, the monarch's chemical defense alters energy flow. Predators that avoid monarchs redirect their feeding toward other insects, changing competitive dynamics and population sizes. Plants benefit indirectly when herbivorous insects are suppressed by predators that cannot rely on monarchs as food. These cascading effects illustrate how a single species, through its survival strategy, can influence entire communities. As autumn approaches and temperatures shift, monarchs gather for migration, their numbers swelling into vast aggregations that fill the air with color. In these moments, the warning signal becomes overwhelming. Thousands of butterflies, each carrying the same chemical message, move together across landscapes. Predators encountering these swarms are confronted not with uncertainty, but with excess. The cost of testing becomes prohibitive. Avoidance is reinforced at a scale few insects can achieve. The monarch's success, however, is never guaranteed. Its dependence on specific plants, its exposure during flight, and the energetic demands of migration all impose risks. The borrowed chemistry does not make it invincible. It makes it predictable in a way that predators learn to respect. This predictability, maintained through honest signaling and consistent defense, is the cornerstone of the monarch's survival. In the end, the monarch butterfly embodies a strategy built on transformation and transmission. Plant toxins become insect armor. Internal chemistry becomes external communication. The warning is not whispered or hidden. It is displayed boldly, carried on wings that drift across fields and continents alike. The chemistry is borrowed, but the message is unmistakably its own. Morning light filters through tall grasses, breaking into narrow shafts that slide across stems and seed heads still damp with dew. Between these vertical lines of vegetation hangs a structure that is almost invisible until the angle is just right. A wasp spider's web spans the gap, its silk threads pulled taut into a precise geometric plane. At the center, the spider waits head down, legs paired in rigid symmetry, its abdomen striped in bold bands of yellow and black. The resemblance to a stinging insect is not accidental, but here, appearance is secondary. The true weapon is already deployed, stretched across the air itself. The web is not passive architecture. It is a living extension of the spider's hunting strategy, designed to intercept motion in an environment where speed favors the prey. Grasshoppers, flies, and small moths move quickly through open vegetation, relying on sudden bursts of flight or leaps to evade predators. The web turns that speed into liability. When an insect strikes the silk, kinetic energy transfers instantly into vibration, announcing the capture before the prey fully understands what has happened. Escape attempts only worsen the situation, tangling wings and legs more deeply as the threads flex and rebound. This is the first half of the wasp spider's two-part system. The web does the capture. It restrains, delays, and exhausts. Its silk is engineered for this purpose, combining strength and elasticity in proportions that allow it to absorb impact without breaking. Sticky spirals hold prey long enough for the spider to respond, while radial threads transmit vibration with remarkable efficiency. From the center of the web, the spider reads these vibrations like a map, discerning size, location, and struggle intensity within seconds. Only after capture is secured does the second phase begin. The spider advances cautiously, never rushing directly into reach of flailing limbs. This hesitation is not fear, but calculation. Many of the insects caught here are capable of inflicting damage. A strong kick from a grasshopper or a bite from a beetle could tear delicate tissues. The web minimizes this risk, holding the prey in place while the spider chooses its moment. When it strikes, it does so with precision, delivering venom through hollow fangs into the prey's body. The venom's role is not dramatic instant death. It is shutdown. Neurotoxic compounds disrupt nerve transmission, causing paralysis that spreads outward from the injection site. Muscles lose coordination, then responsiveness entirely. Crucially, this process takes time. In a free-moving insect, partial paralysis might still allow escape. In the web, there is nowhere to go. The silk ensures that the prey remains immobilized long enough for the venom to complete its work. Recovery is impossible because movement, the only path back to control, has been taken away. This synergy between web and venom is the core of the wasp spider's success. Neither component is sufficient alone. The web without venom would restrain prey temporarily, but prolonged struggle could eventually lead to escape or damage to the silk. Venom without the web would require the spider to overpower prey directly, a risky proposition against fast or well-armed insects. Together they form a system where each compensates for the other's limitations. The web buys time. The venom uses it. Once paralysis is complete, the spider wraps the prey in silk, further isolating it from the environment. Digestive enzymes are injected, liquefying internal tissues that will later be consumed. This external digestion is another form of efficiency. The spider does not waste energy chewing or tearing. Chemistry does the work quietly, while the web holds everything in place. The entire sequence unfolds with minimal movement, conserving energy and reducing exposure to predators. The environment in which this occurs shapes every aspect of the strategy. Open grasslands and meadows are dynamic spaces, swept by wind and filled with mobile insects. A stationary predator here must control not only prey, but also information. The web's near invisibility prevents early detection, while its placement between stems intercepts common flight paths. Even the spider's coloration plays a role, breaking up its outline against the vegetation, while simultaneously discouraging potential predators that mistake it for a stinging wasp. There is a delicate balance at work. The spider must maintain the web constantly, repairing damage caused by wind, debris, or unsuccessful captures. Silk production is metabolically expensive, requiring protein intake that depends on successful hunts. Each web represents an investment, and its placement reflects an understanding of prey movement patterns within the habitat. The spider does not simply spin anywhere. It chooses locations where the probability of interception is highest, aligning its chemical and mechanical tools with environmental flow. Prey species, in turn, evolve responses. Some insects learn to detect subtle reflections of silk and alter their flight paths. Others attempt to cut themselves free using mandibles. Yet even these adaptations are constrained by time. The venom does not need to be instant. It only needs to act before escape is possible. The web ensures that this window remains closed. In this way, the chemical weapon's effectiveness is amplified not by potency alone, but by circumstance engineered in silk. The wasp spider's venom is tailored to its typical prey, optimized to immobilize arthropod nervous systems efficiently. It is not designed to deter large predators or cause pain in mammals. Its function is precise and narrow, reflecting the spider's reliance on its web for defense as well as offense. Large animals blunder through webs occasionally, destroying them entirely, but these encounters are losses the spider mitigates through rapid rebuilding rather than confrontation. The chemical weapon remains reserved for prey, not threats. This specialization reveals a broader principle in predator evolution. Success does not always favor versatility. It often favors integration. The wasp spider does not need the most powerful venom or the strongest silk. It needs both to work together under predictable conditions. The web transforms the chemical effect from temporary disruption into final control. The venom, in turn, ensures that the web's restraint does not need to be permanent. As the day advances, more insects collide with the web. Some are small and subdued quickly. Others struggle violently, shaking the entire structure. Each encounter reinforces the same pattern. Capture first, shut down second, consumption later. The spider rarely deviates from this sequence because deviation introduces risk. Consistency here is survival. Toward evening, as light fades and temperatures drop, the web glows faintly in the low sun, its threads briefly visible before dissolving back into invisibility. The spider remains at the center, motionless once more. The chemistry within its fangs is still potent, but it will not act unless the web has already done its work. In this ecosystem, victory does not belong to the fastest or the strongest. It belongs to the organism that can prevent recovery, closing the gap between capture and control so completely that resistance never has a chance to matter. At the forest edge, where sunlight fractures into gold and shadow, a structure emerges that seems less built than grown. Suspended between tree trunks and understory branches, the web of a golden silk orb-weaver spans open air in a broad, deliberate arc. Its threads glow faintly in the angled light, catching warmth and color in a way no synthetic material can replicate. This is not a trap hastily assembled. It is a biochemical instrument refined by evolution to transform space, motion, and chemistry into control. The spider rests near the hub, legs extended, body aligned with the web's geometry. Every strand around it has purpose. The radial lines provide strength and information, running straight from the center to anchor points that stabilize the entire structure. Between them spiral adhesive threads, laid with careful spacing to maximize interception without compromising airflow. The silk is not uniform. Different glands within the spider's abdomen produce fibers with distinct properties, some designed for tensile strength, others for elasticity, others still for adhesion. Together, they form a composite material that rivals the most advanced human polymers in efficiency. Silk is chemistry made solid. At the molecular level, it is composed of proteins arranged in repeating patterns that balance rigidity and flexibility. This balance gives the web its remarkable strength-to-weight ratio. Strand for strand, golden silk can absorb immense force relative to its mass, stretching under load rather than snapping. When a flying insect collides with the web, the silk yields just enough to dissipate energy, converting momentum into vibration instead of rupture. Escape becomes unlikely, not because the web is rigid, but because it is responsive. Adhesion adds another layer to this system. The spiral threads are coated with microscopic droplets of sticky fluid, each droplet acting like a tiny adhesive reservoir. These droplets behave dynamically, stretching and flowing when touched, increasing contact area as the prey struggles. Humidity influences their performance, and the golden silk orb-weaver adjusts placement and spacing accordingly, spinning webs that function across changing environmental conditions. The glue does not simply hold. It adapts, responding to pressure and movement in ways that maximize retention. When prey strikes the web, the event is instantly translated into information. Vibrations race along the radial lines, their frequency and amplitude shaped by the size, location, and struggle of the captured insect. The spider does not see the prey in the conventional sense. It feels it. Sensory organs in its legs detect minute oscillations, allowing the spider to construct a spatial map of the web in real time. Each thread becomes a data channel, each vibration a signal that narrows uncertainty. This conversion of motion into a map is the web's most powerful feature. The spider distinguishes between debris and prey, between harmless leaf litter and a struggling insect worth pursuing. It can even infer risk, identifying insects that may fight back or possess defenses of their own. The spider waits when necessary, allowing prey to exhaust itself against the silk before approaching. Patience here is not passivity. It is strategy informed by continuous feedback. Once the spider commits, the approach is precise. It moves along radial threads, minimizing disturbance to the adhesive spirals that hold the prey. The strike is targeted, delivered exactly where paralysis will spread fastest. Venom plays its role, but it is not the star of this sequence. The chemistry that truly defines success is already in place, woven into the structure itself. Without the web's ability to restrain and inform, venom alone would be unreliable. With it, the outcome is nearly certain. The golden silk orb-weaver's web also interacts with the environment in subtle ways. Its coloration reflects and absorbs specific wavelengths of light, making it visible to some insects and nearly invisible to others. This selective visibility may increase capture rates by exploiting the visual biases of flying prey. In open forest edges where light conditions change rapidly, this adaptability becomes critical. The web is not just strong, it is optically tuned to its surroundings. Maintaining such a structure requires constant investment. Silk production demands protein, which must be obtained through successful hunting. Damage from wind, rain, or large animals necessitates repairs or complete reconstruction. Each morning, the spider evaluates its web, recycling old silk by consuming it and reusing the proteins to spin anew. This recycling underscores the efficiency of the system. Nothing is wasted. Chemistry loops back into itself, sustaining the spider's ability to rebuild night after night. The web also functions as an early warning system. Large disturbances send broad, chaotic vibrations that prompt the spider to retreat or drop from the web entirely, avoiding predators that blunder through the structure. Smaller, rhythmic vibrations signal prey. The spider's survival depends on interpreting these patterns correctly. Mistaking a predator for prey could be fatal. The web reduces this risk by amplifying differences, turning raw motion into intelligible signals. Insects caught in golden silk rarely escape. The combination of adhesive droplets, elastic threads, and strategic spacing ensures that each struggle increases entanglement. Wings adhere, legs stick, and the more the prey fights, the more information it provides to the spider. There is a grim efficiency to this feedback loop. Resistance accelerates resolution. The chemistry embedded in silk transforms effort into vulnerability. Beyond predation, the web shapes the local ecosystem. By selectively removing flying insects, the golden silk orb-weaver influences pollinator movement, herbivore pressure, and even plant reproduction. Its presence alters the behavior of insects that learn to avoid areas dense with webs. Over time, these patterns affect species distribution and interaction networks. The web is not just a trap, it is an environmental modifier. The spider itself remains largely unseen, its body secondary to its creation. This inversion of focus reflects an evolutionary truth. For the golden silk orb-weaver, the web is the primary interface with the world. The spider's anatomy supports silk production and vibration sensing because those functions deliver the greatest returns. Venom is precise and effective, but it is the web that determines when and where venom is used. As evening approaches and the forest dims, the web takes on a different character. Moisture in the air enhances the adhesive droplets, increasing capture efficiency. Nocturnal insects begin to fly, and the web becomes active once more. Each collision sends a ripple outward, a message traveling along golden lines toward the waiting spider. The laboratory is open. Experiments unfold in real time, governed by physics, chemistry, and behavior. In this system, chemistry extends beyond toxins. It defines material properties, sensory translation, and environmental interaction. The golden silk orb-weaver does not merely deploy chemicals inside its prey. It externalizes them, weaving biochemistry into architecture. Motion becomes data. Data becomes decision. Decision becomes control. By dawn, the web may be torn, rebuilt, or reinforced, its form shifting with conditions. Yet the principles remain constant. Strength without excess, adhesion without rigidity, sensitivity without exposure. The web stands as a testament to what chemistry can achieve when it is not confined to glands or fangs, but spun into the world itself, turning empty space into a map where every movement has meaning. Heat presses down on the forest in thick layers, settling into bark and leaf alike. By midday, the air vibrates with more than temperature. It carries sound, a rising, relentless chorus that swells and contracts as if the landscape itself were breathing. Cicadas cling to trunks and branches, their bodies aligned with the vertical grain of wood, wings folded neatly along their sides. They do not hide. They announce. In doing so, they reveal a different kind of weapon, one that does not pierce or poison, but overwhelms perception itself. The cicada's call begins deep within its abdomen, generated not by vocal cords, but by a pair of specialized membranes known as tymbals. These structures buckle inward and snap back repeatedly, driven by powerful muscles that contract with astonishing speed. Each click is small, but in rapid succession they merge into a continuous tone, amplified by the hollow chambers of the cicada's body. What emerges is volume on a scale rarely matched by insects, a sound capable of carrying across fields and forests, bending around obstacles and saturating the acoustic space. This is not noise without purpose. The call is precise, tuned to frequencies that travel efficiently through warm air and dense vegetation. It is loud enough to drown out competing sounds, including the wing beats and movements that predators use to locate prey. For birds and small mammals that rely on auditory cues, the cicada chorus creates a problem. Direction becomes ambiguous. Individual signals blur into a wall of sound. Targeting one insect within the mass becomes difficult, sometimes impossible. From the cicada's perspective, this is the point. Survival here is not about avoiding detection entirely, but about altering the predator's decision-making process. A single cicada calling alone might draw attention, Thousands calling together flood the environment, transforming clarity into confusion. The predator's sensory systems are overloaded, forced to process more information than they can resolve into a clean target. The result is hesitation, miscalculation, and often abandonment of the hunt. This phenomenon is known as signal warfare, and it relies on principles that echo through ecology. Predators are limited not only by speed or strength, but by attention. Their nervous systems evolved to filter signals efficiently, prioritizing those that indicate opportunity or threat. When the signal density exceeds that capacity, filtering fails. The cicada exploits this vulnerability, using sound as a means of defense by saturation rather than concealment. The effect becomes most dramatic during mass emergencies, when periodical cicadas surface after years spent underground as nymphs. At once, entire populations appear, climbing vegetation to molt and take flight. The sudden abundance shifts the balance of power. Predators cannot consume enough individuals to make a meaningful dent. Even when they feed heavily, the vast majority of cicadas survive long enough to reproduce. The calls that fill the air during these events do more than attract mates. They announce excess. In these moments, sound alters predator behavior at a fundamental level. Birds that would normally forage methodically become selective or overwhelmed. Some feed until satiated and then ignore cicadas altogether. Others retreat to quieter areas where prey detection is easier. The chorus reshapes the acoustic landscape, carving out a temporary refuge defined not by walls or toxins, but by volume. At the physiological level, producing such sound is costly. The muscles driving the tymbals consume significant energy, and prolonged calling increases metabolic demand. The cicada compensates through a life history strategy that prioritizes reproduction over longevity. Adults live briefly, focusing their remaining energy on calling, mating, and egg-laying. The cost is high, but the payoff is collective success. By synchronizing their activity, cicadas distribute the burden of defense across thousands or millions of individuals. The chemistry enters the story more subtly. Sound production depends on muscle performance, which in turn relies on biochemical processes that regulate contraction speed, endurance, and recovery. Cicadas possess adaptations that allow sustained, rapid muscle use without immediate fatigue. Their bodies manage heat generated by constant activity through behavioral positioning and wing movement, preventing overheating during peak calling periods. Thermoregulation here is not passive. It is essential to keeping the signal going. Predators experience physiological strain as well. Continuous loud noise elevates stress responses, increasing heart rate and diverting attention from precise hunting. In birds, auditory overstimulation can interfere with the processing of visual cues, further degrading targeting accuracy. The chorus does not physically harm predators, but it taxes their sensory systems, pushing them toward decisions that favor avoidance. There is irony in this arrangement. The cicada is not armed in the conventional sense. It lacks venom, stingers, or chemical sprays. Its body is soft, easily consumed, yet it survives not by being dangerous, but by being disruptive. The call changes the rules of engagement. Predators must decide whether the effort required to isolate and capture an individual is worth the reward. Often, it is not. This strategy also influences interactions within the ecosystem beyond predator and prey. The sheer volume of sound affects communication among other species, temporarily suppressing birdsong and altering insect signaling. Some animals adjust their activity patterns, shifting feeding or mating to quieter times of day. The cicada chorus becomes a temporal force, reshaping behavior across the community while it lasts. When the calling finally subsides, the forest feels altered. The sudden quiet is almost startling, as if a pressure has been released. Predators resume normal foraging, but the cicadas are already gone, their reproductive work complete. Eggs rest in tree branches, nymphs drop to the soil, and the cycle resets. The memory of the sound lingers, but its function has been fulfilled. What makes this system remarkable is how it blurs the line between communication and defense. The cicada's call evolved primarily as a mating signal, a way to locate and attract partners across distance. yet its defensive value emerges as a byproduct of scale and synchronization. Chemistry and communication intersect here, not through toxins, but through the biochemical machinery that enables sound production and endurance. In the broader context of survival strategies, cicadas demonstrate that altering perception can be as effective as causing damage. Predators are not defeated physically. They are persuaded, overwhelmed, and redirected. The decision not to attack becomes the victory condition. This reframing highlights a central theme across many species. Survival is often about influencing choices rather than enforcing outcomes. As evening approaches and temperatures drop, the chorus softens. Individual calls become more distinct, then fade entirely. The forest returns to its layered soundscape of wind, birds, and insects. The cicadas that remain cling silently to bark, their role complete. The chemical processes that powered hours of sound slow, muscles relax, and energy reserves are spent. In the end, the cicada's lesson is clear. Not all weapons puncture or poison. Some flood the senses, bending behavior through excess rather than force. Chemistry underlies the ability to communicate at scale, and communication, in turn, becomes a shield. In a world shaped by decisions as much as by damage, the loudest voice can sometimes be the safest place to stand.